Good afternoon, everybody, and welcome to this afternoon's session. We are working on Greek time rather than classical time tonight. So this session is entitled The 100th Anniversary of Quantum Science and Technology. That's a very big topic. I am Professor Sir David Payne. I am and have worked for 60 years in photonics, which is the science of light. And for those of you that are not scientists, light is quantum. By definition, it's made from particles. Well, it has a duality. It's a wave-particle problem. And these two gentlemen, very distinguished speakers, that will occupy you for the next 1.5 hours, have the challenge to explain light and quantum and all its peculiar effects to you. And I have told them that the rules of this session are that there shall be no equations. And that makes the challenge even greater. So I'm very much looking forward to this session because although it's my field, I will also learn along with you. So our first distinguished speaker is Jean Iliopoulos, a corresponding member, Academy of Athens and the French Academy of Sciences, a former professor of theoretical physics and currently honorary member of the Laboratory of Theoretical Physics, École, Normale, Supérieure, Paris. Professor Iliopoulos.
Well, thank you very much, especially Christos, for this very great idea of having this thing. I think I would lift up. Here it is. So, Koinon means something we all share, something meant to unite us. In our world, most things or ideas divide people, mostly with tragic consequences. Science, art, culture are among the few things that can bring us together. The Academy of Athens was well inspired to name this new institution Koinon. Let us have the dream, I have a dream, let us have the dream that it could be the seed of a new koinonia in which art, science, culture, bring people together, become the links to unite people. For those of you who will think that I'm talking utopia, let me add that it's not necessary to hope in order to undertake, nor to succeed in order to persevere. This comes from Guillaume d'Orange. So, from classical to quantum physics. The trouble is that there are many parallel stories. There is not just one time where quantum physics was invented. It was done in many parallel stories, independent one from the others. And I say, mostly beyond the textbooks. I quote my late friend Okun, who was saying, it's amusing how little the authors of textbooks know about the history of physics. It's true that if you read a textbook on quantum mechanics, you rarely find the correct story. You find the story that the author has in mind, which has been developed by his learning of the stuff, but you don't learn the history of the stuff, right? So, as I say, there are many parallel stories. Let me give some. The first was Planck, Einstein, de Broglie, Schrödinger, and then Dirac, etc. So this is one line of thought. The other was Balmer, Rutherford, Bohr, Sommerfeld, Heisenberg, Schrödinger, Dirac, etc. Eventually, it was Dirac who showed that these two gentlemen, I can't say anything. Well, I have something, I will. That Schrödinger and Heisenberg were in fact talking about the same thing, although their language was totally different. Right? Then there's a third story, which is De Broglie, Dirac, Feynman, etc. And the fourth story, which is De Broglie, Einstein, Bohr, John Bell, etc. So there are four different stories that they go intermingled one with the other, and that makes the story very complicated, but also very interesting to see how it goes. Now, a word of caution. This talk will be one on the history of physics, but is given by someone who is not a historian. Right? I'm not. Feynman was saying that scientists make fools of themselves every time they talk outside their field of expertise. Since history of physics is entirely outside my field of expertise, this talk may prove that once more Feynman was right. Okay. So after this introduction, let's go to the... So the limits of classical physics. By the end of the 19th century, classical physics was at a turning point. I don't say crisis or something because it doesn't mean very much, but it's a turning point. A rare combination of great technological innovations for the time, for this time, the 19th century, and together with progress in fundamental theoretical ideas. So this combined had made a marvelous scientific scheme. One, classical mechanics had reached a state of near perfection through the works of Newton, Lagrange, Hamilton, etc. In fact, it was really, I would say, the archetype of physical theory, science. Every other field of physics aspired to look like classical mechanics because it was perfect. At least that's how it looked. On the other hand, classical electromagnetism had achieved a profound unification of electric and magnetic phenomena through the work of Coulomb, Ampere, Faraday, Maxwell, etc. And it culminated with its formulation what we say today, a classical field theory. So it became classical mechanics, but a system with an infinite number of degrees of freedom. So it was classical mechanics, right? In parallel, there were also powerful mathematical techniques, mainly through the study of partial differential equations, which made possible the to obtain calculations, precise and accurate predictions in agreement with measurements and observations. And the last thing that I want to mention is the formulation of statistical mechanics by these people, Carnot, Clausius, Boltzmann, Maxwell, Gibbs. This, I will come back to that. This was really a fantastic thing. You will see what I mean. It was really the thing that really pointed out that where the thing would go. So, a certain degree of optimism was probably justified at that time. And I quote, it was by Michelson, the famous experimentalist who measured first, tried to measure the motion of Earth through ether, right? Say, it seems probable that most of the grand underlying principles have been firmly established. An eminent physicist remarked that the future truths of physical sciences are to be looked for in the 6th place of decimals. It's not known who was the eminent physicist Michelson was referring to. Some named William Thomson, Lord Kelvin, but there is only some vague circumstantial evidence about it. There is no evidence that ever Lord Kelvin expressed such an opinion. I can tell you the circumstantial evidence later if you want. It's not interesting. Yet, several cracks started appearing in the edifice, in the classical physics edifice. And I will mention some which, however, you see, I see them now, more than 100 years later. It was not clear that the moment these cracks were appearing, people realized that there was a crack. So this is the mistake that we amateurs of historians, we make. We interpret old results by present knowledge. This is wrong. You should not do that. Right? So, but anyway, I'm not a real professional historian, so it doesn't matter if I make this mistake. Now, motion of the Earth through the ether. This, I will not talk about that because it's part of another revolution. It's not the one we are going to talk. But it was an important thing. People were trying to measure how Earth could move through ether. And Michelson was one of the persons who tried that. But then, Balmer series. This was 1885. Right? So much before what we call quantum physics, right? And if you think today, how could a classical system have discrete energy levels? Now, of course, at that time, they did not think, they did not know that these were energy levels. They were looking at absorption and frequencies of absorption and emission. But even that, a classical system cannot have discrete values because a classical system is a classical mechanics, so the variables are Q of x and t and p of x and t. They are continuous variables, so every observable is function of these continuous variables. So you cannot have anything that is. If you have this discrete spectrum, it means that the quantity, whichever it is, now we know it was energy, but whatever it is, has a matrix representation, because that's what is discrete, right? So a matrix representation means two matrices don't commute. So it means non-commutative geometry somewhere. But it was not realized for many years. It took 50 years before people realized that the phase, in quantum mechanics, in the phase space, there is a non-commutative geometry, that momenta and positions do not commute. But it was there 50 years ago, right? Almost 40 years ago. Right. Definition of the entropy in statistical mechanics. That's another great story, because the entropy was, well, Carnot was the one who tried to, you see, it was what I was saying before, great technological progress was heat engines. The first heat engines were there, and people tried to get the best heat engine, right? So Carnot was studying precisely how to make the optimum heat engine, and formulated this equivalence between heat and work, right? Joule was the one who first formulated the principle of energy conservation, right? And then Clausius introduced this strange notion, entropy. What is entropy? He found this tropy, the Greek word, and N, from energy, he took N and then added tropy to make it entropy. But it was not clear really what it was, and he introduced it as a measure of how chaotic a system could be. So this was but it was not very clear and not precise. The first person who gave a precise definition was Boltzmann, and that was in 1877. And he gave several, in fact, Boltzmann was a fantastic writer. I have to confess I never succeeded to understand what he was saying, because he was very obscure. But in fact, I discovered that I was in good company, because Maxwell who was an admirer of Boltzmann, also complained that he could not understand his papers. So it's now Boltzmann gave several definitions of entropy, and one of them was the one I have here. It's one of the few equations I write, where entropy is some constant, which is called the Boltzmann constant, times the logarithm of a quantity which he said was the number of states that are available to the system. But what is this number of states? In a classical system, infinite, obviously. And apparently he was aware of that, because there is a cryptic remark somewhere in 1877 in which he says in the paper something that you need some small energy epsilon. He puts the term epsilon, the symbol epsilon there. But he doesn't elaborate what he meant with this. Right? So you see, there were cracks, as I said, but nobody was really aware that something was cracking. So Lord Kelvin apparently had understood some of these things, because in 1900 precisely, he was giving a talk in the Royal Institute of Physics, and he said, I quote all his thing, "The beauty and clearness of the dynamical theory which asserts heat and light to be modes of motion," he was referring to Maxwell, "is at present obscured by two clouds. The first involved the question, how could the Earth move through an elastic solid such as essentially is the luminiferous ether?" So that was the first problem. The second is the Maxwell-Boltzmann doctrine regarding the partition of energy, which is the energy levels I was saying. So somehow he had the intuition that these two, in fact, if you, in retrospect today, we can say that the two great revolutions of the early 20th century, relativity and quantum theory, are directly connected to these two clouds. He had identified these clouds as being potentially important, and they were. Yeah. So, now I start a different story, which the 19th century saga of the light bulb. You know, we usually learn in books that light bulbs were invented by Edison. It's not true. Light bulbs, the first light bulbs were built in the beginning of the 19th century. In fact, it was in England. Most of the story was, in fact, in England. And people were trying, you see, what is a light bulb at the beginning? It was some filament, something, some material, which was heated by an electric current, and heated a lot. But when you heat a material like that, you usually make it red. It's like when you light a fire, right? So when you light a fire, it's very good to heat you. If you go very hot, it's very hot, but it's not very good to read. It doesn't give you much light, right? It gives you heat, but not light, right? Because that is when you burn things. That's what happens, right? And in fact, even today, not today's, there's no more. But 20 years ago, most of us are older than 20. I can't see any lower than 20 here. So most of us remember the light bulbs, the incandescent bulb. And you remember that the part of energy that you were consuming that goes into visible light was around 5%. All the rest was heat. Right? So they were very good heaters, but very poor lighting devices. So it was search for more light and less heat. So this was the saga. So that's what people tried. And they tried many things. They changed materials, and then they understood they should raise the temperature. But if you raise the temperature, normally you burn the thing. So you have to put it in inert gases. So it created a whole branch of research, even fundamental research, right, which was connected to this search for more efficient light bulbs. A byproduct, which turned out to be interesting for our story, was to motivate physicists to study the interaction between the electromagnetic radiation and matter. So this is, most people started looking at this problem as a byproduct of the effort to produce better light bulbs. In 1860, that's why you see that the story goes much earlier than Edison, which was 1900 something, that the first invention of the thing has started much earlier. In 1860, Kirchhoff introduced, now for those of you who had studied electrical engineering, certainly you know Kirchhoff, because it's Kirchhoff's laws are fun. Everybody who's an electrical engineer knows that, knows Kirchhoff. So Kirchhoff introduced the concept of an ideal black body. Now, what was a black body? A black body is a body which is supposed to absorb all radiation, right? That could, and say, to visualize it, imagine, well, I have to find something to point. So, look at that here. Right. Imagine a cavity, metallic or something, with a very small opening. Okay? So if, no matter if you send some radiation here, it will start getting reflected everywhere, but it has very small chances to get out. Right? So it takes many reflections before it gets out, and therefore whatever comes out has lost memory of what was when it came in, because after all these reflections, it had been degraded. So black body is this body that absorbs everything and then emits something which has nothing to do with what it absorbed, right? So, in 1893, Wien discovered a law. Both it's empirical and with theoretical arguments, but also empirical. And the law is the following. He said that whatever radiation comes out from a black body, right, which is, as I said, is universal somehow, it has nothing to do with the one that went in, has a form which looks like that, right? This is the wavelength, so this is, you see, small wavelength means high frequency, and large wavelength means low frequency. Right? So it has some curve like that with a maximum, and the maximum depends on the temperature of that cavity, which is, and it goes, you see, it goes to smaller and smaller wavelengths, that means higher and higher frequencies, when the temperature increases. Sunlight is around a little bit over that. And so it is and the visible light is around here. So it's not surprising, obviously, our eyes have been adapted from evolution to be most sensitive to what the sun sends us as radiation. A creature that could not see sunlight would have much chances of survive, right? If the main source of light on Earth was sun, so that was the thing. So this was the Wien's law. And then people started thinking, how could we compute this spectrum? And I have here several. One of them was Lord Rayleigh, who made a computation which was very good here at, say, low frequencies, large wavelengths, but totally wrong at high frequencies. And it was Ehrenfest who cornered the expression ultraviolet catastrophe, which has remained ever since for quantum field theory, for the ultraviolet catastrophe, we say, right? And apparently it was Adam first. So in 1900, Planck tried to do the same thing, to compute this spectrum, but then he had the idea of starting to compute the entropy as defined by Boltzmann. You have this system of radiation inside the cavity, and wanted to apply Boltzmann's formula, and then he found that nothing could be done like that. Now, you see, Boltzmann tells you that the entropy is how many states, how many ways you have, since you have a certain energy, total energy is fixed, so you have a certain total energy, how many ways you have to distribute it into whatever, say, Planck called them resonators, that you could have, say, the cavity was supposed to have, say, atoms or something that would resonate with this thing. Now, I give you an example. Suppose that you win today in the lottery, and you win 100 euros. Now you are generous, and you say, oh, I have 10 friends, I will give them this 100 euros. But you only have one banknote of 100 euros. That's all you have, right? So how many ways you have to distribute this 100 euros to your 10 friends? Well, 10. You can give it to one or to others, since you only have one banknote, right? Now, if instead of having one banknote of 100 euros, you have two banknotes of 50 euros, you have more possibilities. Because now you can give 50 to the one and 50 to another one, right? So you have not only the possibility of giving 100 to each one, but also all the pairs of friends, which are 45 or whatever. So you have 55. If instead of having two banknotes of 50, you have 10 banknotes of 10, then the possibilities become very many, because then you can give to 3, to 4, to some, all possible ways. If instead of that you have coins, say 1 cent, so 10,000 1 cent coins. You want to have many possibilities, right? But you see that as you decrease, you have smaller and smaller units of money, right? If you could go to half of cents or tenth of a cent or hundredth or millionth of a cent, then the number of possibilities explodes, well, more, it's faster than exponentially, it's factorially, right? And eventually, of course, if you want to have a finite number of possibilities, you must have a minimum amount of money. You cannot have arbitrarily small amounts of money if you want to have a finite number of possibilities. That's what Planck found, that you must have somehow a minimum amount of energy that you can exchange between the radiation and the cavity, otherwise the entropy will be infinite. So in Planck's, I call them the unwilling revolutionary. He made a revolution, but he did not want to have a revolution. Planck was a classical physicist and wanted to remain classical physicist, and he discovered that somehow energy should be minimum quanta. You cannot, he called it, quantum was introduced this way, that you should not have arbitrarily small amounts of energy. The same way that you should not have arbitrarily small amounts of money if you want to have that. So this was the beginning, and he said that the energy should be proportional to the frequency, and the h is a constant. He introduced this constant. He even computed the order of magnitude of the constant. So it was the first introduction of discrete grains of energy, or quanta of energy. As far as I know, neither Planck nor anybody else understood at the time that this strange assumption signaled the most extraordinary revolution in the physical sciences. It was really a revolutionary idea, but nobody understood at the time. The next actor was Einstein. Einstein was in 1905, which is called the Annus Mirabilis for Einstein, because it was in 1905 that did everything. Special relativity, the photoelectric effect that I talked now, Brownian motion, everything were done in 1905. So I will discuss only one of those things, the photoelectric effect. Photoelectric effect had been discovered much earlier by Hertz, who observed that we may obtain an electric current by sending a beam of light on a piece of metal. You just send a beam of light and you obtain an electric current. Einstein, during his famous Annus Mirabilis, Einstein studied this phenomena, and he was the first person who took Planck seriously. So he said, well, I assume that Planck was right, and the exchange of energies between light, electromagnetic radiation, light, and metal are done in pieces of energy, right? In grains. The word photon was introduced much later in 1926 by a chemist by the name of Lewis. So he derived these special laws of the photoelectric effect that are strange laws, that if you want to have more current, you should increase the frequency, not the intensity of the light. It's the frequency that counts, not the intensity, because that's how you obtain more. And in fact, these laws were verified in 1915 by Millikan, who's a great experimentalist, one of first very great experimentalists of this period, who in fact started, as he says himself, wanted to check these laws to prove that Einstein was wrong, because these laws sounded incomprehensible. To increase the current, you have to increase the frequency and not the intensity. Strange. The intensity should count. No, it's the frequency. And he verified the laws, of course, to his great surprise. And this gave Einstein the Nobel Prize in 1922. Contrary to what you may think, Einstein never got a Nobel Prize for relativity. He got the Nobel Prize for the photoelectric effect. There has been no Nobel Prize for relativity ever. Nobody ever got one. So, 1909, Einstein writes a very cryptic sentence in one of his papers, which the translation is mine, it's in German. The next phase of theoretical physics will be a theory of light which could be interpreted as a fusion between a theory of waves and one of emission. These are his words, waves and emission. So now we go to the synthesis of all that. That was de Broglie. De Broglie is a story all by himself, if I start telling you, because it's another crazy man. I mean, strange character, but anyway, the talk today is not for that. In 1922, de Broglie rediscovers Einstein's results, but this time under the explicit assumption, he writes, I also translate from French myself, that electromagnetic radiation consists of atoms of light. He calls them grains of energy. He calls them atoms of light, atomes de lumière. Right? Atoms of light, each one with energy h nu. Right? So by this assumption, he rediscovers all Einstein's results. And in 1923, he makes the great and crucial step. He says, if to an electromagnetic wave, to normal light is supposed to be an electromagnetic wave. It's described by wave equations, but so it's a wave. If to an electromagnetic wave we can associate quantities which characterize corpuscles, why not do it the other way around? So it's normal to attribute, he says, it's only normal, to attribute also a wave to a particle. So this was the first time that this wave-particle association was made, and that was 1923. He applies this principle to electrons bound in an atom, and he finds the Bohr-Sommerfeld quantization rules. Because he said, well, when the wave goes around, the phase should come to the same thing, should change by 2 pi, right? So he applies that to bound electrons, and he finds the Bohr-Sommerfeld quantization rules, but goes one step further. He applies it to free electrons. Now, if free electrons move in straight lines, right, like all free particles. But if you have also a wave that describes that, waves interfere. So he predicts interference patterns for electrons. This was discovered experimentally in 1928, and gave de Broglie the Nobel Prize in 1929. It was the first Nobel Prize given for this new quantum mechanics. Heisenberg, Schrödinger, etc. got it later. 26, Schrödinger writes the equation describing the propagation of de Broglie matter waves. It took him some time, but that's technical. Why between 23 and 26, what was he doing for 3 years? The equation is almost trivial to write. Well, he was looking for a relativistic equation and could not write it because he could not. And in desperation, he took the non-relativistic limit and found Schrödinger's equation in 26. With its probabilistic interpretation, it became one of the pillars of modern quantum mechanics. So this is precisely 100 years earlier, right? Now, in the meantime, was the other stories that I told you before, Balmer series and Rutherford, Bohr. Rutherford gave the first atomic model, right, as you know. Bohr and Sommerfeld gave this quantization rules. Forget all that, I go faster. So, I will say nothing about the number 2. I only saw one thing about number 3, which is interesting, and then I will go to number 4 and finish. Now, number 3 is best explained by Feynman in 48. So it started with de Broglie, and then Dirac, but then Feynman. And then Feynman, if you read Feynman's lectures in physics, introduces quantum mechanics this way. Say, forget about everything else you know, and you make this double slit experiment. And the experiment, he says, you do it once with bullets, you fire bullets, once with waves, and once with electrons, and you see what happens. So with bullets, well, you fire bullets, you see this is the probability of having, if only one hole is open, you will have stuff like that. If this hole is open, you have something like that. If both holes are open, you get the superposition of the two. With waves, so the thing, bullets is, each bullet produces a single impact on the screen and the probability sum. Right, okay. Now, you do with waves, there is no single impact. You send acoustic waves or whatever, there is, you can say it can have one particular point, the acoustic wave goes everywhere, and then you obtain these interference patterns that you have here, right? You do it with electrons. Where is it? Oh, yeah. The bullets on the left do not form interference patterns, the waves do. Then you do the same thing with electrons, and I go very fast. You find each electron makes a single impact. However, you obtain interference patterns as if they were waves. So electrons have this strange schizophrenic behavior. when they are materialized as impacts on a screen, they behave as classical point-like particles. But their propagation is described by a wave equation. These are the experiments, by the way. And you can see you fire one electron, here it is. More electrons, blah, blah, blah. More electrons, and finally you obtain these interference patterns come one after the other. It's not one electron after another, and they form interference patterns nevertheless. Right? This is the thing. Does God play dice? This was the famous question by Einstein. Because this is a probabilistic thing, how come that electrons know one has left many, say, seconds or even hours before that they should go there and not here to form the interference pattern? The probabilistic interpretation explains that, but Einstein doesn't like it. He said, God does not play dice. That was his thing. And then you say, is quantum mechanics a fundamental theory? And then you start, well, in the double slit experiment, through which hole did the electron goes, etc. So Einstein and Bohr had for many years a long correspondence, which is a marvelous thing to read, because these two giants exchange their ideas, and it's fantastic, absolutely. Well, in our reckoning, Bohr won the argument. But in 1935, Einstein went back to the Einstein-Podolsky-Rosen paradox, which introduced a new concept, in which the paradox was somehow explained this way. It's not realistic, but that's simpler to explain. Imagine you produce two photons. Photons are polarized one way or another, right? And you know that the two polarizations should up to make zero, because the initial thing has no spin, right, in this particular experiment. So you know that they should. So Einstein, Podolsky, Rosen say, well, suppose that you produce these two photons and they travel far away, right? According to quantum mechanics, they are in a superposition, right, of spin like that and spin like that, or spin like that and spin like that. But if you measure one, automatically you know what happens to the other, very far away, right? This was made, even if driven apart, the two photons remain correlated, that's what it says. So, in quantum mechanics, a two-particle phase is not always equivalent to the sum of two one-particle states. The correlations are important. So 2 may be more than 1 plus 1, let's say. A hidden variable theory is a theory in which somehow the particles are independent, but they depend also on variables we do not know and we cannot measure. Now, nobody can exclude that. After all, you cannot claim that today, in 2026, we can measure all variables. There may be variables that escape our measurement. Right? This created, for many years, a discussion that had degenerated into sterile philosophical considerations with no interest whatsoever. Even great physicists participated in this nonsense. Until 1964, John Stuart Bell succeeded to bring the question back to physics. He proved that no theory with local hidden variables can reproduce all the predictions of quantum mechanics. And he gave examples of predictions that cannot be reproduced by hidden variable theories. Again, this has remained for some time theoretical, but then the three, Alain Aspect, Claude Clauser, and Anton Zeilinger, independently took up the challenge and proved that quantum mechanics was right. They obtained the Nobel Prize of 22. Anyway, so let me continue. Quantum mechanics has the reputation of being incomprehensible. Is it true? Maybe all revolutionary theories appeared incomprehensible when they were first proposed. Newton, that one body may act upon another at a distance through a vacuum without the mediation of something else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Letter to Richard Bentley in 1687. Today, Newton's law does not sound incomprehensible to most of us. Are we much smarter than Newton? No, we just get used to the idea. Quantum mechanics looks incomprehensible because we are not yet used to it. When we start teaching it at high school, at elementary school, or whatever, it will appear perfectly normal. Conclusion. We often talk about the revolution of quantum mechanics. It is true. Like the Industrial Revolution, the one of quantum mechanics has influenced profoundly our everyday lives. Telephones, these very instruments we are using, telephones, GPS, internet, you name it, they all are due to quantum mechanics, right? It would be more correct to use the plural to talk about the quantum mechanical revolutions. Nor are we yet at an end. We are still actively involved in it, and we are looking forward to even greater discoveries, and I hope that Emmanouil will talk about them. Thank you. Sorry for being late.
Excellent. Professor Iliopoulos, you may not be a historian, but maybe you should have been a historian. That was one of the best expositions of the history of how we got from classical to where we are today, with a lot more to come. So I think you also emphasize an important point. The journey is not over. We're in the middle of it. And that is possibly what makes it somewhat incomprehensible to some of us. But our next speaker hopefully is going to continue with this journey and let us welcome then another distinguished speaker in the area of quantum physics, which is Professor Emmanouil Floratos. He is the Academy of Athens, of the European Academy of Science, and a Professor Emeritus of Theoretical Physics at the University of Athens. So, the name of his talk is IT from Qubits, the Universe as a Quantum Computer. So over to you, Professor Floratos.
It's a great honor for me here to present in this inaugural meeting of the Koinon of Academies. Thanks especially to Professor and colleague in the Academy, Professor Christos Zarefos, for giving me the opportunity to present some thoughts about the link of quantum mechanics and information theory. Okay, this is the great painting by Raphael, and it is the emblematic painting that we use in the Koinon of Academies, where you see all the great philosophers of the antiquity, but also of the Middle Ages come together in this picture. And I think this is what we are doing now, that of course we are not so great as they were, but we try our best to open dialogues for the progress of science, and I hope peace in this world. So the plan of the talk has several items. I will discuss first the general idea, then I will discuss the quantum revolution, application of quantum mechanics, some general information. I will spend more time describing the notion and the methods to measure information. What is quantum information, quantum computers, and at the end some visionary opinion of John Archibald Wheeler, a Princeton physicist, who introduced the idea and the philosophy that everything in nature, that is particles, space-time, and all the forces, all the fields we measure, come especially from measurement, and not only the results of measurements can be always be given in terms of bits of 0 and 1s, and in more modern times by qubits. So essentially, our universe is participatory, and there are no phenomena without the observers. This is a very strong statement, of course, philosophical statement. He was the inventor of many notions of the black holes, of the quantum measurement and information, and he's considered by many as the father of quantum information. Okay, now the abstract is about this famous phrase, from bit. The only truth we can know about nature is nothing else than the information we get in terms of zeros and ones. That is, nature can be represented by strings, huge strings of 0 and 1s, and all the information is in these strings. Okay? But we don't ask questions. That is, if we don't make experiments, then we have, it's impossible really to understand anything about reality. So somehow exclude by this phrase the philosophical thinking. You need experiment to understand physics. He had more strong points on this phrase, that the universe itself is created by the observation, okay, which is more philosophical. Now, Big Bang is what is it? It from Qubit is all the universe. And the universe which was created by recent data, we know that was created by something like 14 billion years ago. And it contains all that it contains in all places in the universe, as far as we know. Atoms, nuclei, and nuclei are composed by quarks, and which are essentially the mass of the universe is contained mainly in the quarks, and then we have the leptons, and then we have the gauge bosons, which are the forces which give the interaction of all these particles. Okay. Now, as was explained in this very nice and informative talk by Professor Iliopoulos, the quantum was introduced by Max Planck as the energy light quanta. The first objects were the energy light that he was studying, and he understood, for the reasons that Professor Iliopoulos explained, that mass consists of quanta, and this happened in the beginning of the 19th century. Then Einstein used the notions of but not only for the propagation of the light, but also for the emission from an absorption of photons from the atoms, okay, and from particles. So he showed somehow, for the first time, the particle nature of photons. Then de Broglie introduced the wave-particle duality in 1921-22, and then after that, Heisenberg was the first to introduce quantum mechanics, somehow a theory where all the observables which we measure in experiments are matrices, are not numbers, and they are non-commutative. And his main point was that when we observe by particles, some other particles, we cannot measure at the same time the position and the momenta of the particles. So he proved that there is an uncertainty in this measurement between the position, the momentum, whereas the minimum product of the uncertainty between position and momentum is the h, the Planck's constant. Now Schrödinger introduced the wave mechanics, which essentially follow the line of the Broglie discovery. And then Dirac introduced quantum mechanics for the relativistic, for the special relativity, that is for particles which move with velocity close to the velocity of light. But then he had to introduce new particles. For the electron, for example, he had to introduce the anti-particle, the positron. And then the positron was discovered later. Now, this created a philosophical debate between Einstein and Bohr, and Bohr already in an article in 1927, he explained the notion of complementarity, that is, there are pairs of observables that we cannot measure, so we cannot have all the information, so we cannot decide really what is the value of both observables at the same time. So it's a kind of indecidability that is introduced by measurement, by quantum mechanical measurements. And also that the quantum mechanical measures determine the particle or wave nature of matter. We may have experiments that they are explained by the particles, or experiments like the diffraction experiments, which are explained by waves. Now, of course, quantum mechanics then introduced to smaller scales, to nuclei, and the fathers of this nuclear force research started with Fermi and Heisenberg, and this, of course, created a lot of applications later. I will discuss this in the next transparency. But around 1935, there was a paper by Schrödinger that two quantum systems which are far apart and they don't interact, still they are entangled. That is, one influences the other, so we can exchange information, but not energy. Information simultaneously, information for both systems. And then Einstein, Podolsky, and Rosen devised some experiment that Professor Iliopoulos described to see that quantum mechanical description is not complete. But then Bohr wrote again in 1935 an answer to this criticism of Einstein, that completeness of nature of quantum mechanical physical reality is restricted under the experimental findings, which are the uncertainty relations. Okay, you cannot forget the experiment that it is true the uncertainty relation and then say if it is complete or not complete the description. Okay, I have some pictures of these heroes: Heisenberg, Schrödinger, Dirac, and then various applications of quantum mechanics. Of course, people did not know in the beginning of the century that radioactivity essentially comes from quantum mechanical behavior of the nuclei. Then in the 30s, we discovered the nuclear fission, and a nuclear power reactor was constructed by Fermi, and later we had the atomic bomb. Okay, in the end of the 30s, nuclear magnetic resonance, which is a very important diagnostic tool for medicine, was discovered, the phenomenon, in experiments by Isidore Rabi. And of course, what is very important for the later development of computers and communications was that the discovery quantum mechanical tunneling effects between two states of a system by Sake and collaborators in 1957, the tunneling diode which made possible the transistor, and now we have the extreme technological constructions of transistors which are something around 1 nanometer long, okay? And okay, I refer here also to another discovery by Josephson about the superconducting junction, which has a two-state, is a quantum mechanical two-state system, but the important thing is that it is a macroscopic system. Okay, so it has quantum mechanical behavior, but it is macroscopic. Now we have the superconductivity from quantum mechanics explanation, Nobel Prize by BCS theory, superfluidity. Much later, there were Nobel awards in physics to Aros and Wineland for cavity QED experiments, where they succeeded to manipulate single atoms in electromagnetic cavities. And essentially what was the fantastic result of this experiment, they could manipulate the electrons around the nuclei of the atoms, so they make Keplerian orbits. Okay, quantum mechanics has different orbits. They are not orbits like, you know, the planets around the sun. They succeeded to observe and to manipulate the electrons so they make trajectories around the nuclei, which is exactly the classical behavior. And then the last and very determining technological development for the construction of quantum computers is the discovery by Martinis, Clark, and Devoré, Nobel physics in 2025. They constructed quantum circuits which are composed out of many, many elements. So they are macroscopic, a few nanometers wide. And the whole quantum circuit was put into superconducting state, and they succeeded to measure the energy levels, and all this macroscopic quantum circuit, which can manipulate information, had discrete energy levels. So they demonstrated first that it is possible to have quantum mechanical systems which are macroscopic enough to manipulate information. Okay? Now, the other theoretical direction was the study of the information by itself, and the story begins with Kurt Gödel, who said that in axiomatic arithmetic systems of logic, which is the basis for manipulation of information of computer science, we cannot have completeness. We have incompleteness theorems, and there are statements that you cannot prove in an axiomatic system of logic. But not only that, but also the second theorem was saying that if you give me a theorem, I cannot check if this theorem is complete or incomplete in this axiomatic system. Okay, then Alan Turing was the basic inventor of the theory of computation, and he tried to solve also problems of mathematical logic by proving results of Gödel by using theoretical machine, which was the Turing machine, and he made a very detailed theory of algorithms. So the problem was for the theory of algorithms, which algorithm will stop or will not stop? Can we prove a theorem, which is an algorithm? or not. He showed the equivalence between his results and the results of Gödel. But in 1948, he had the first ideas, and then in the beginning of the 50s, he introduced the notion of intelligent machines, which is the first papers in artificial intelligence. Now, in the beginning of the 40s, because of the need for manipulating big amounts of information for military purposes, John von Neumann constructed the first modern computer, and he was a great mathematician known about the mathematics. He constructed the mathematical foundations of quantum mechanics, the mathematical foundations of game theory, and also of some kind of algebra which are used in mathematics and analysis, which are called von Neumann algebras. In 1948, Shannon introduced it was one of the first people to say that essentially the information is something that it is possible to measure, and he obtained studying the transmission and the detection of information. He introduced the notion of Shannon entropy, which is a measure of information which has very close resemblance with the entropy of thermodynamic entropy. Because the various signals that you send have a probability distribution, and using this probability distribution, you can construct this Shannon entropy, which is a measure of it. Now, the next step in the line of relation with physics and information was the discovery of Rolf Landauer, an IBM physicist, who was the first to study in the beginning of the 60s the thermodynamics of information. So he introduced the notion that since computation uses energy for erasing and writing information, you need a least amount of energy, which is essentially the energy you need for manipulating one bit of information. And in an environment of temperature T capital, the energy you need is K, the Boltzmann constant, times T times log 2, which is 0,022 electron volt. Now, today's supercomputer, they have, per bit, they consume much bigger energy, which is 10 to the 9 Landauer bounds. And while the biological processing is far more efficient, but it's still far from the bound, it's 10 to the 4 times the Landauer bound. Now this opens the door for studying more carefully, if possible, to manipulate information by quantum devices, so we decrease the consumption of energy. Now, with the advent of big data due to internet, we have huge installations of manipulating trillions of bits per second. This is one picture of the Google big data center in Santa Barbara. And one of the biggest producer of data, the amount of data per second, are the results of experiments at CERN, where the millions of small counters in the detectors measure the passage and the energy of particles which come out after the collisions of the beams. This is one of these big detectors. This is the CMS detector, open to eye. And you see that there are millions of small circuits with millions of pixels, and they measure the passage of particles. Now, the idea that how you can systematize information theory inside the framework of quantum mechanics was initiated by Richard Feynman in the beginning of the 80s, and he introduced some quantum gates, which they act on qubits, and through these gates, operations on qubits, you can represent the evolution of a physical system under a particular Hamiltonian, which is an energy, quantum mechanical energy of a system, and the system evolves according to this Hamiltonian. Okay, he was the first one to propose this idea of quantum information, and this later was systematized at the theoretical level, constructing the corresponding axioms to the axioms of information theory of Turing and Church and others. It was Deutsch in England. He introduced the notion of the quantum Turing machine, which is a universal machine. Universal machine means that this machine can represent any other machine like itself, and so you can calculate any possible algorithm with this machine. Okay. Now, there are many interesting problems in materials, science, weather prediction, earthquakes, medicine, genome application, etc. But the problems are very hard computationally. So it is hoped, and already there are some results, first results, that with quantum computers you can solve some of these problems in polynomial time and not in exponential time. And also for brain research, this is Mr. Richard Feynman, and was the first paper in 1982. Now, after Landauer, around 1990, the first revolution, if you like, in quantum information came with the work of Shor, who was looking. He was working. He had education in physics, quantum mechanics, information, etc. He had a lot of studies before he discovered his algorithm. He was looking for the possibility to break the cryptographic codes, which are called the RSA code, for example, where essentially the codes compose of the product of two huge numbers, prime numbers. Prime numbers are numbers which are not divided by any other integer by exactly themselves. And you have, for example, one prime integer of 200 digits, and then another one, and then you multiply and you have a huge number. You use this huge number now as a cryptographic key, but this key can be broken only if you know these two factors. The problem of factorization of huge integers is one of the hardest problems, and classically the time is exponential. And there are algorithms classically, but for example, 300 bits, 300 decimal place integers were broken in the beginning of the 2004-2005 by the collaboration of 5,000 computers around the world, which coordinate their efforts to break with the classical algorithms. But you can imagine much bigger numbers, and then the need for quantum factorization was obvious. So he introduced the first such algorithm. He proposed this algorithm in 1994, but there were some loopholes in the proof, and then in 1996 he completed the proof, and now he is considered somehow the algorithm that he opened the revolution for quantum computers in order to make this experimentally possible. Okay? So the progress was slow by constructing first qubits. The qubits quantum are small, if you like, are small devices that you can store information which have two possible states, 0 or 1, but quantum mechanically you can be at the same time at 0 or 1. And you have probability, if you measure this quantum device, you can find the result will be 1 with some probability or 0 with another probability. And how to construct this? The first realistic experiment that created some kind of macroscopic, nanoscale, macroscopic device was by Martinis. I said that before also. He constructed superconducting qubits, quantum circuits, and he observed that between the energy levels that were discrete, he observed also that it is possible to have tunneling effects between one level and the other level. So they observed also the macroscopic tunneling effect for this. Now, after years of, this was shown experimentally in 1985. Several years ago, around in 2000, they presented the first quantum computer quantum circuit with 58 qubits, and they could manipulate information and show that they could solve some difficult mathematical problems in few hours. Sorry? Yes, there, yes, thank you, yes. I think this was the 2020, I think, 2020, not and they succeeded to show that they could solve a difficult mathematical problem in a few hours, while the best classical algorithm would take several years. Okay, so that's why they've got the Nobel Prize. And in general, Qubit is a physical system. Okay, it's not some abstract. It's information theoretic notion, but in practice, it's a physical system. It is any two-state system which you can control quantum mechanically. Maybe this is the helicity of a photon, the polarization of the photon, the spin of the electron, the spin of an atom, etc. Okay, this is the guy, Martinez. And this is the 2023 is one of the most recent photos that they have of 70 qubits. This is a quantum computer, and all this is the electronic circuitry. And this quantum computer is put inside liquid helium at a temperature of 3 degrees Kelvin. So, I mean, all this experiment cost millions of dollars. Okay? It's not easy to do it in a laboratory, university laboratory. Now, the universe is a quantum computer. So where we go from there, I mean, to some more theoretical directions. In theoretical physics, there is an intense activity which is called the last few years in the United States. There are several, all the big universities in the United States are in this collaboration. It is a big program of $10 million, and it's called It from Qubit collaboration. What these theoretical physicists try to do, they have shown in various papers in the previous years, but also recently, that the space-time geometry, gravity, and all physical forces are emergent, are not something fundamental that we have to start from their equations or their measurements directly. They are emergent from something quantum mechanical, which is the entanglement. is the entanglement, is the relation between two far away quantum systems. Okay, so if you have many degrees of freedom, like field theory, then a ground state of field theory has infinite degrees of freedom. So they try to calculate for finite amount of degrees of freedom, but very big amount of degrees of freedom. They calculate the entanglement of this system with separating this big system into two subsystems. So how much information contained in this ground state is how much entangled is one subsystem to another subsystem. Okay, when you do these calculations, they found something very strange, that this gives you something like, which is geometrical, somehow it's a geometrical area in a curved space-time, then varying these subsystems, the extent of these subsystems and the content in degrees of freedom, they succeeded to show that even the gravitational theory of relativity, that the Einstein equations can be derived as equations from these entanglement measures. So essentially, the it from Qubit came to become real. I mean, this idea of John von Neumann that finally is the entanglement, which plays a role. And through entanglement, you can represent all physics we know. This is the vision. And further research is going on. And the direction, now it is called EPR, means Einstein, Podolsky, Rosen, which is the experiment that shows the entanglement to two faraway systems, quantum mechanical entanglement of two faraway systems, that it is equal, is identical with general relativity. That is, we understand now the other way around. We understand classical theory, which is well described by known mathematics. Okay, Riemannian geometry and measurements have proven that it is a correct theory. With it is the same thing with the entanglement content of some quantum systems. So I think that this direction of research is very, very important, and it is followed this collaboration in several other countries. Also in Greece, we have some collaborators that also with John Iliopoulos, we discuss these things, and we try to have new ideas to understand better what is all this, etc. Okay, so thank you very much.
Well, thank you so much for that, Professor Floratos, and thank you to both of our speakers for keeping to time so brilliantly that we actually, for the first time in this entire symposium, have some time to spare. So that allows us to actually have a couple of questions if there was somebody here. And I have a gentleman there who you're very welcome to ask your question.
We try to discuss speed of light, ignoring that neutrinos exist. Okay, in the same way that you cannot compute speed of sound without knowing that molecules exist, in the same way, actually, the mass of the molecule enters the equation for the speed. The same thing applies here. You need the mass of the neutrino. And we've published this, we've done it, it's very simple. You need the mass of the neutrino, you put it in the same equation where you put this, compute the speed of sound, and you find C. This is all I was trying to tell you.
What is the question?
The question is this.
Could you use the microphone,
compute
please?
The speed of sound. Yes.
No, I did not.
Thank you. But we're trying supposedly to educate younger people and to inform our colleagues. Sorry for this.
Okay, thank you for your question, or more of a comment, I think. We have another one here.
Thank you very much both for these very illuminating lectures, but Manolis, I try to follow this story with Google's quantum computing, and then after this, the first revolution, and then the second with the 70, I thought that there would be then, since the main problem, because quantitative difference I thought would be simple, so I was expecting an immediate impact. Why hasn't it happened? Is it economics? What is the reason? What is the reason?
You see, it is what I tried, but I was very fast to say what is an entangled state. Right, an entangled state is a state of two particles. Most of what has been done until now are photons, in fact. So you have two photons that have been produced some way, not the way I showed, some other way. They have been produced in a quantum state of two particles, and then you try to move them apart. Now, they remain entangled as long as there is no other interaction with something else. And this creates a big problem. So the last person I mentioned in this series of people with Zeilinger has succeeded, but using all this modern technology, not the 80, but today's technology of fiber optics, to send kilometers apart. And they remain these two particles remain entangled. But still, it's only two photons. Now, if you want to have a large number of particles to make it large, well, technically, in principle, it's possible, yes, but in fact, I don't I have discussed with great experts, experimentalists in this field, nobody dares to predict any time, say that, yes, in 5 years, in 10, in 20, in 30, in 50. Nobody dares to do that. Yes.
Yeah, if I could comment from the chair for that, although it's not my field, so forgive me, the experts. My understanding is that a real usable computer comparable to today's digital computers requires millions of qubits, and we are not there yet. And as you scale up the qubits, you also begin to have a problem with error correction, which begins to take more and more of the power. And so this is what pays our salaries, folks. So you should be very glad that there is a lot of research yet to do, but it's very exciting. Do we have one last question then? Right, we are being told that our time is up. So thank you all to the audience and to the speakers for a fascinating session.